Perception of light is caused by the photoreceptor of retina. There are three kinds of photoreceptors called L, M, and S cones. Human brain perceives color from such three stimuli. Color perception can be represented in XYZ color space. Human perceives light whose wavelength ranges from 400 to 800 nanometers. Light multiplied by color matching function becomes the XYZ value after integration. Light is an energy which distributes continuously with respect to the wavelengths. So, different spectral distributions are sometimes perceived as same colors. These two patches appear as the same color under a certain light, but they appear as different color under another certain light. The observed RGB value is shown here. Left two patches are same color but right two patches are different color. For example, let us think about two virtual paints shown here. Spectral distributions on the right are derived when illuminated by the light on the left. Such spectral distributions are multiplied by spectral sensitivity, which result in an XYZ value after integration. In this case, two paints are perceived as same colors. Let us illuminate these paints with different light. Two paints become the spectral distributions shown on the right. Such spectral distributions are multiplied by spectral sensitivity, which result in an XYZ value after integration. In this case, two paints are perceived as different colors. We want to excite the metamerism using two lights and three paints. We mix multiple paints to excite the metamerism. Our purpose is to automatically estimate the mixing ratio of paints. Using a particular example, we explain our reflection model of mixing paints. Suppose that the reflectance of paint number 1 is denoted as D1. If the light reflected 10 times at ingredients, the reflectance per one reflection will be a 0.1 power of D1. Suppose that the reflectance of paint number 2 is denoted as D2. Suppose that the light passes the same path. Let us mix 70% paint number 1 and 30% paint number 2. If the light passes the same path, the reflectance will be D1 to the 0.7 power multiplied by D2 to the 0.3 power. Denote the spectral reflectance of paints as D1 to DNP. Denote the mixing ratio as W1 to WNP. Define D to the W power to be the reflectance of mixed paint. Then illuminate the mixed paint by the light E. Finally, XYZ value is obtained by multiplying by spectral sensitivity P. Suppose there are three paints DW1, DW3 and DW2. Under the light E1, the paint DW1 and the paint DW3 are aimed to be same. Under the light E1, the paint DW3 and the paint DW2 are aimed to be different. Under the light E2, the paint DW1 and the paint DW3 are aimed to be different. Under the light E2, the paint DW3 and the paint DW2 are aimed to be same. Here, we minimize the left top term and the right bottom term, and we maximize the right top term and left bottom term. So, the cost function to be minimized becomes like this. The term to be maximized is raised to 0.5 power while the term to be minimized is raised to twice power. Human perception is sensitive to slight difference of color. So that's why we weighted the terms that makes two colors same, heavier than other terms. Here is the result of the mixed paint computed by our method. Under blue light, the upper arrow heading left is only recognized. Under yellow light, the lower arrow heading right is only recognized. In the future, we are planning to use our method in the application field of art, advertisement, or watermark.